I first met Song when I think he was a student around 50 years ago when I first got to the Institute. And now he's a big shot, having done so many wonderful things in the intervening time. It's hard to keep track of all of them. And he's going to tell us today about correlators and amplitudes in energy force reading.
For the introduction, and really glad to be back here. Thanks for the invitation to this wonderful workshop and the opportunity to talk. So the keywords in the title is correlators. And I want to, so this is also relatively new for me to something to work on. And I want to use this opportunity to invite some of you who are interested to think about these objects, because the amplitudes simply just follow from correlators. So if you care about amplitudes in this theory called n equals 4 super mules, planar n equals 4 super mules, then a correlator is really the king, that the master object that contains all the amplitudes to all loop level at any multiplicity and so on, in principle. And I want to go through mainly three aspects of these correlators in n equals 4 super mules. The first is really interesting method that explored some graphs that have been called F graphs. So I want to talk about the graphical aspects and some combinatorics of this so-called F graphs, how they play an important role in computing these correlators to very high loop level. And then the quite crucial part is that these correlators can be understood from some geometrical point of view, which is we still don't have a satisfying object that's just called correlahedron, which at least to myself is still not a totally satisfying object to define and compute forms. Actually, the part for computing form is more satisfying, but there's still some issue even with the very definition. And at least you can see that this definition reduced to something called squared amplitude, which is some geometry that's even simpler than the amplitude, the loop amplitude. And also talk about how to go to the tree amplitude squared in some different limit. And finally, if I have time, I'll also come to some, because everything I will describe in these talks are about integrands, loop integrands of correlators and amplitudes. So in the last part, I'll also mention something about how to integrate them, which will be giving you some numbers and functions, as you've heard from Jake's wonderful talk. That'll be another version of things that he talked about, that how can you perform these loop integrals. And this will be based on some recent work with wonderful collaborators, Canxin, Yichao, Yaoqi, Xuhang, and Qinling, as well as an earlier paper with Yuting and Jiakai. Okay, so again, every talk, many talks here in this workshop start with kinematics. So we're very familiar with this kinematics for amplitudes. Here I'm talking about planar case. So I'm sure many of you know that you can, instead of thinking about this momentum of the planar amplitudes, you can also think about these dual points where every momentum is given by the difference of the two dual points. So this momentum conservation corresponding to a closed polygon in this dual space. And since we are considering massless case, each edge of this polygon is light-like, is square to 0. And this is actually the basics for going to the momentum twisters introduced by Hodges, that you can view every point here as a bitwister from two neighboring momentum twister I-1 and I, so that every edge here also corresponding to a twister. So that's the basic kinematics we're very familiar with for planar scattering amplitudes. Now, what about correlators? So for correlators, you don't have momentum. Everything lives in the coordinate space. So you directly have some points. And unlike in this case, they don't form any polygon because they are just off shell. So every xij square is just non-zero. So you just think about correlator as depending on, say, 4 arbitrary points. So don't worry if you don't know the physics jargon about correlators or this theory. The whole point of this talk is that you don't need to know them. Still, you'll be able to understand them from a mathematical point of view. So, but I'll still just say that we're computing something called half BPS correlator, which is given by this local operator of trace phi square, the simplest case. This of course is very important not only for amplitudes, They also play a role in ADS-CFT and many other things. And this 4-point correlator is just a function of these 4 points, which if you extract some prefactor out, is something that depends on 2 variables. These are the 2 cross ratios formed by these 4 points. I call them V and W. And very nicely is, of course, a permutation invariant under these 4 points. Unlike in the amplitude case, it's a cyclic object. Now you have a permutation object that's invariant under the permutation of the 4 points. And I'll mainly be talking about the perturbative expansion where the tree level is normalized to 1, and then at loop level, at each L loop, you're dealing with some function of 2 variables, GL, V, and W. Okay, so actually, what we mostly care about in this talk is loop integrands, right? As we are very familiar with from amplitudes. What is the loop integrand for the amplitudes? The L loop amplitude is given by some rational function integrated over this loop variables, which you have y1 all the way through yl. So this object is also symmetric in the loop variables. Of course, for the external variables, it's cyclic, but for the loop variables, it's permutation symmetric. And that's how you also start the loop amplitude hedron by introducing just L arbitrary lines in twistor space, right? Unlike the external objects given by this intersecting lines in twistor space, the dependence on loops is given just by L arbitrary bitwistors, L lines, usually called AB in this space. Now for correlator, the story is actually easier because your external dependence is also permutation invariant. So why don't you just define this object that depends on all the 4 plus L points, 4 of them being external, L of them being the loop variables, and integrating over x5 all the way to x4 plus L. Actually, after you strip off some prefactor, there's a beautiful work that people understood more than 10 years ago that this integrand, this f that depends on 4 plus L points, is a function that's completely permutation invariant under symmetric in all these 4 plus L points. And in principle, they are computed by Feynman diagram. These Feynman diagrams are very, very complicated, even more complicated than the amplitude case. So so far, there being this 4-point correlator. This object has been, the integrand has been computed up to 3 loops using Feynman diagrams. So that'll be something that depends on 7 points, permutation invariant in all the 7 points. And as I'll come later, that one of the reasons we care about this object is that we'll take some Light-like limit, some limit when this x starts to become xij squared to 0, this so-called Light-like limit. This will reduce to amplitudes, the square of amplitudes. Okay. So our task is very clear. We want to find a function of these 4 plus L points, symmetric in these 4 plus L points, rational function. And since there's a conformal symmetry, this function has weight minus 4 in every point because you're integrating all this d4 of this x. Right? So for the whole thing to be conformally invariant, it has to have weight minus 4. So this is very nicely represented by the so-called F graphs. So you have some graph that depends on L plus 4 points. The first case being one loop, this 5-point, some graph that has 5 vertices, and it has to have valency 4, right? Because every edge here represents a xij squared in the denominator. So this is just the 1 over all the xij squared, the first case. This is the complete graph for the 5 points. So you learn the first thing that at one loop, there's no computation to do because there's just one graph that satisfies the permutation invariance and the weight 4 condition, right? Actually, it's also true for 2 loop. That's the only graph you can draw that has 6 vertices and valency 4. And if you want, this single graph is representing this. Sorry, I mean this graph is not. I mean this graph is representing a permutation sum of all the permutation of the 6 points. So the expression is actually as follows. Okay, so a single graph representing all the permutation of all these vertices with valency 4. And there's a normalization factor. There's a symmetry factor that we want every term that here appear with coefficient 1. Okay. So starting 3 loops, this is no longer true. You can have more than one graph that has this property, but we consider a special limit. We consider, as always, the number of color goes to infinity. So it has been conjectured that in this limit, this limit, that everything that can all the graphs that can contribute to the planar correlators are these planar F graphs. So again, at 3 loops or 7 points, if you ask it to be a planar graph, there's again just one of them. Of course, now you start to have a numerator, this dashed line. When I talk about planar graphs, I refer to its denominator structures. So this graph is actually given by all the solid lines with 1 over xij squared and a dashed line with a numerator sitting on it. So it's not just valency 4. It has a net valency 4 because these 2 blue vertices has valency 5, but I have a numerator that cancel the reduce the weight by 1. Okay. So again, this single graph represents a summation of 7 factorial terms in this way. So the game here is really just to write down all possible F graphs. I mean, for the simplest case, we just do planar graphs, and then ask what are the coefficients in front of. There's some number accompanying these graphs. These numbers cannot be determined just by this remarkable permutation symmetry and conformal weight. It has to come from some physics. So as Jake and the collaborators have worked on this problem many years ago, that they've achieved really a great deal, that they found some graphical rule that allows them to determine these coefficients all the way up to 10 loops. So graphs with 14 points. So you can see that for planar graphs, this grows really fast. Like when you go to 14 points, it's almost a million planar F graphs. And the job, all the physics input is to determine their coefficients. Here's an example for 4 loops, which has 8 points, right? Still, you only have 3 F graphs, and you from some constraint I will describe now, that you can fix their coefficient to be +1, +1, -1. So what are these constraints? One of the simplest but also most powerful constraints is this so-called square rule. So whenever you find your F graph has this substructure with a square and another points connecting to the 4 corners of the square, you should relate this coefficient of this graph to a graph that you remove this points in the middle. Okay, and if you remove these points in the middle, of course you change the weight of these 4 other points. So you actually need to add these 2 cross here, right? But since this graph starts with some numerator, so the numerator could cancel this either one or both of these diagonals. Actually, that's needed because if you have a structure that has no numerator in it, then you will end up with some non-planar graph, right? So that would be saying, okay, if I have a graph that just look like that without any numerator, the coefficient has to be 0 because this graph should have the same coefficient as a graph, n-1 point graph, which is non-planar. The non-planar graphs are all excluded in this bootstrap. Okay, so that being said, the square rule is just the rule that connecting coefficient of a n-point graph to a coefficient of n-1 point graph, so which is very simple, but it cannot apply to all graphs because some graphs don't have any structure like that. Then it doesn't say anything about it. I mean, it still fixes really a lot of graphs. You can see the 10 or 11 loops it fixed like more than 90% of the graphs, the coefficients recursively, but the remaining you still have a lot of work to do. So there are more graphical rules that Jake and collaborators found, which allow you to finally bootstrap the whole thing. This graphical rule is coming from the fact that the correlators contain, for example, the square root comes from the fact that correlators contain 4-point amplitude square in it. Okay. So, for example, if you apply it to the for loop case, the square root allow you to fix 2 of the 3 graphs, but the last one you have to use some other rule that I'll mention. So 5 loops is similar. Out of the 7 graphs, you still have 1 coefficient that cannot be fixed by square root. So the main progress we made just a few months ago is that we found a single rule. There's a new graphical rule, which is closely related to the fact that there's some physics motivation behind it, but in the end, it's also very closely related to the fact that it's related to amplitudes. And from this single rule, we are able to bootstrap the, just forget about any previous rules before, just this single rule, we're able to bootstrap the F graphs up to 11 loops, the correlator. And we have a conjecture that maybe this is sufficient to all loops for planar case, but that has, we don't have evidence beyond 11 loops. So I don't want to go in through the detail of deriving this rule. This rule amounts as a universal behavior of the correlation function that you take some cusp limit. Namely, you take x12 squared and x23 squared at the same time. So for the physics audience, if you take the whole thing, there's this argument that the correlator should go into Wilson loop or amplitude squared. Now I'm just using the same argument, but only taking the minimal light-like I can do, just two of them, which form a cusp here, right? So the basic logic is that if I take this two light-like limit, which is only possible in Lorentzian signature, I can derive a rule like that. So basically, I forget about all the physics behind it, but the rule is just saying for every F graph that contains a double triangle, you pinch a double triangle and so this diamond with a diagonal, you pinch these 2 points, you reach and then add another line here, you reach at a cusp, right? So every graph that can reduce to a cusp has to be related to the cusp diagram. So this is the relation between them, and the equation is really saying, you know, sorry, the equation. The equation is really just saying the sum of this. Sorry, the equation is just really saying the sum of all this endpoint graph that has double triangle structure, when they reduce to this cusp, on the right hand side, n-1 point graph has only one. So all the sum of this coefficient of the endpoint graph should reduce to the coefficient of n-1 point. So here is some example. You look at this guy. It has a double triangle structure here, right? And you do the pinching. The pinching reduces it to the 5-point guy, the unique guy, but with this cusp structure. You can go to 7-point. There are several different double triangle structure that allows you to reduce to the same 6-point graph, but with the different positions of the cusp. This graphical rule is saying the sum of this coefficient should equal to the same 6-point coefficient. Okay. So even going to 8-point, this is everything, right? We have 3 graphs here, and you find all the double triangle and do the pinching. You have actually a unique graph, planar graph at 7-point. So this equation is saying this graph should reduce to the unique coefficient, C2 equals B1, and this graph, C3, also equals to B1. But there's an interesting equation that this graph, C3 and C1, they can both reduce to some non-planar graph, okay? You start with planar graph, but after the pinching, you reach at the non-planar graph, which has coefficient 0. So it's just saying C3 and C1 add up to 0. So this is the equation for three loop case, which you find that it tells you that once you know the 2-loop coefficient, which is normalized to 1, this 3 coefficient of 3 loop is fixed to be 1, 1, and -1. But it's really interesting that you go to higher loops, this linear equation is not only allow you to solve the n-point coefficient in terms of n-1 point, it also gives very strong, it also constrains the n-1 point ones, right? So actually, so far, when we go all the way up to 11 loops, you can see that it fixes all the C, which are n-point coefficients, and all the B, which are n-1 coefficients at the same time. So it's always sufficient to fix both the L loop and L-1 loop at the same time. So you may wonder that maybe there are some graphs that's missed in this operation. Indeed, starting 8 loops, the first time starting 8 loops, and then you jump 9 and 10 loops, they're fine. But then 11 loops, you see you see more. So there are some graphs that has no double triangle in it. So naively, these graphs are not captured by the pinching rule I have. But exactly as I said, you can go one loop higher, and every graph should have a cusp in it, at least, right? So all the higher, if you go one loop higher, you will see this invisible graphs as this lower loop guys appearing in your equation. Since your equation allows you to fix both the L loop and L minus one loop one, so that's how we proceed. We don't need any other rules and fix the coefficients of these graphs uniquely. So here is just some statistics of the coefficients. You see some very interesting phenomena. Of course, I mean, you may have the impression that this coefficient up to 5 loops I introduced you, they are all +1 or -1. But if you go higher, you go to 6 loops, 2 phenomena happen. First, you see a 2. Okay, there's a unique graph that has coefficient 2. And also you start to see some F graph that has vanishing coefficients. I mean, that's really this 0 starts to dominate when you go to higher and higher loops. So for example, you go to 9 loop, it has 75% of the coefficients are 0. 10 loops is 85%, and to 11 loops, out of 20 million graphs, only 2 million graphs survive. So I think this is still there's still some room for improvement, which is how can you recognize all the zeros from the beginning? Like what are the patterns that tells you the graph should be 0? That we still don't know. And also you see that these are also not just integers. Starting 8 loops, you see some a half. 14 loops, you see a quarter, and so on. So this might be explained from our equation, since sometimes we have a 2 in the equation. But I want to draw your attention to this unique graph that has the largest coefficients. So at every even loops, there's some unique graph that has a coefficient that's the largest in magnitude. For example, you have this 2 at 2 at the 6 loops, -5 at 8 loops, and 14 at 10 loops. So you may wonder if this is Catalan, that the unique graph at even order. I mean, this graph is very special. This graph looks like this so-called anti-prism. You can draw some n-gon and connect them in this way. So this is the 6.1. This is the 8.1, 10.1, 12.1. They have coefficient -1, 2, -5, and 14. But now we have the ability to analyze actually the next one, the 12th loop, or 16-point ones, because you don't have to go through all the coefficients, all the bootstrap for the 12th loop ones. You can analyze some local system. So you can ask, since this guy is very symmetric, its pinching give you some odd point graph, which is non-planar, so you should have coefficient 0. You can ask the question, what are the even point graphs that can pinch to this unique odd point non-planar graph? The answer to this question has been understood to all number of points. So you can set up this system. So for example, at 16 loops, there are 142 graphs that are reduced to 0. So their sum should give you 0. So all you need to compute is not like millions of graphs at 12 loops, but only 141. That allows you to deduce this answer, which is not 42, not -42, but -38. So this is some sequence we don't that'll be very interesting, because this is a sequence that also appear at tree level squared. As later I'll mention that in the tree level squared story, there's a constant piece that's exactly this coefficient. So in principle, we should be able to understand this coefficient constant piece also from tree level. Okay, so I've talked about how to bootstrap these correlators. This is the F graph story. It's very strong, very powerful graphical rule that allows you to connect higher loop ones to lower loop ones and eventually bootstrap them. So now let me tell you how these are related to amplitudes. And actually, that's also behind some other graphical rule like the square rule and so on that people have considered in the past. So the relation to amplitude is very simple. You just take the 4 plus L point correlator, this integrand that's symmetric in all the 4 plus L points. You pick 4 points. You pick 4 special points and take like limit, consecutive like limit, like x12 square, 23 square, 34 square, and 41 square to 0. This should be equal to a 4-point L loop amplitude squared, which is defined like this. By squaring amplitude, I literally mean I'm taking the 4-point L prime loops and the L minus L prime loops and summing over all possible L prime. Okay, so in this example, we see that the five-point correlator, if you take 4 of the points and take the Lie-like limit, that gives you a one-loop amplitude. As many of you are very familiar with, the one-loop amplitude is a box integral. Okay, and then this 6-point correlator, if you take this limit, it gives you the 2-loop amplitude, which is a double box, but also one-loop square with the correct coefficient, this box square. These are the 2 possible inequivalent 4 points you can choose to take Lie-like limit. And also, you can see from here that it's very direct to take just the piece with L prime equals L, which is the L loop amplitude, not amplitude square, because all you need to do is to take the 4 points that has no points inside. So just the 4 facets which will of the graph, which will give you the if you only take the contribution from those 4 faces, it will directly give you the 4-point amplitudes. So for 4-point amplitude, it's very special that not only the square is contained in a correlator, but also actually the 4-point amplitude itself is contained in the correlator. What about higher point amplitude? For higher point amplitude, all you need to do is to take Lie-like limit of n more and more points, right? So for 5 particles, you just take a pentagon Lie-like limit, all possible pentagon Lie-like limit. This will give you amplitude square that's even more interesting. The amplitude square now not only summing over a different loop level, it also needs to sum over helicity sector. Remember that the amplitude is parameterized by not only number of particles and number of loops, but also this k, which is helicities. And by starting 5 points, there's non-trivial helicity sectors that the square of the amplitude not only means that you're summing over different contributions from loops, but also you are taking every nk MHV amplitude multiplied by its parity conjugate and summing over all the k. Okay, so let's go to the other extreme. Why don't we just go to the extreme that I take all the points forming all the 4 plus L points forming a Lie-like polygon. That should give me the tree-level amplitude square. Okay, now there's no summing over loops, but I'm literally taking like the cross section in the physics jargon, the MHV amplitude times the MHV bar, next MHV times next MHV bar, and so on, and add them up. Okay, so the tree-level amplitude is given by this, and I can, for convenience, I define the ratio, which is the tree-level amplitude divided by the MHV times MHV bar, which is just MHV bar. The MHV bar is given by the top form of the Grassmannian, which is just an overall thing. So you can see very beautifully the tree-level amplitude squared can be extracted from this F graphs if I take the all possible n-gon limit. Let's look at 6-point. So for 6-point, there are 2 possible n-gon ways of drawing n-gon. One of them just give you 1. They exactly remove all the edges here. The other give you this graph, which still has 2 edges remain and created some dashed line. So this is a very beautiful formula for the square of the 6-point amplitudes, divided by, of course, divided by the overall G26 form. So this 1 corresponding to the MHV times MHV bar. This 3 cross ratio, okay, this cyclic sum of 3 cross ratio is nothing but the 6-point next MHV squared divided by the MHV bar. So here are the 7-point example. So I just want to mention that this function, this n-gon limit of your correlator give you some beautiful rational function, conformal invariant rational function of the xij squared. So this function is actually much simpler than tree amplitudes because the tree amplitude depends on this Grassmann variables and so on. So if once you square it, you're just dealing with some very nice conformal invariant functions of xij squared. And a challenge, I think, is how to compute this function of xij squared to all multiplicities. I mean, right now we can get it up to 15 points because we have F graphs up to 15 points. But I think this is not the best way to do it. I mean, there should be some other way, for example, from geometry to do it. And why do we care about this function from physics point of view? Because this function is just the splitting function, which has many in the collinear limit. It's just the splitting function, the cross section in the collinear limit. It has many applications. One of them is if once you integrate over some energy variables in this object, you get the energy correlator. So the function depends on the remaining angles and so on. And for example, this function has very nice soft limit that if two of the dual points pinch, it just becomes 2 times. This 2 comes from the square of the tree amplitudes. Okay, so just observationally, if you take, for example, the BCFW form of the tree amplitudes and square it, you get something really horrible, because first of all, you need to you take a super amplitude with its parity conjugate. You need to extract the Grassmann degree. You need to extract some MHV bar overall thing. But more important, this function naively term by term has all these crazy spurious poles. But what we are really after here, is a function that only has physical pole, the simple pole in this xij square, which is this local form of this splitting function is what's useful for us. So let me just show you an example. For 6-point tree, this tree square is defined by the MHV bar plus half of the next MHV square. The MHV bar is the top form of G26. In this notation, I'm just writing the numerator as a 6 bracket. And the next MHV amplitude, which I need to square, are given by the sum of some R invariant, some Youngian invariant, if you want, which I define, for example, 1, 2, 3, 4, 5 looks like that. I mean, most of you are familiar with this. Now the challenge is I want to square this guy. I want to take the tree amplitudes and square them. So there's some calculation to do that when you have some fermionic product, you need to convert them always to this proportional to the top form of G26 multiplied by some bosonic things, right? So you can do that. For example, if you take the R invariant 1 and 3 divided by this MHV bar, you get this cross ratio. But the problem is that this cross ratio in momentum twistor space, this has spurious poles in it, right? So now you have to square everything, and after you sum it over all the terms, you reach at this beautiful formula, which is just the local cross ratio U14 defined in this way, plus it's cyclic. Okay, so I would say that there should really be some direct understanding of the squared amplitudes rather than going from the squaring the tree amplitudes, because the answer is much simpler than individual tree amplitudes. And for example, BCFW form completely obscure that the final answer is local. So 6-point answer is just looking like that, and 7-point answer is just the 3 dihedral Cs together with some. So for 7-point, you need to do the next MHV multiplied by its parity conjugate. And after a lot of work, you simplify it to this beautiful product of cross ratios. Well, from F graph, you just directly extract this guy graphically. But that's something, that's a lot of work when you bootstrap the F graph. So it's really, I want to ask a question. Can we compute this tree level amplitude squared? I mean, we're very familiar with tree amplitudes from tree amplitude hedron, say. But can we compute directly the square of the tree amplitudes from some geometry called squared amplitude hedron, right? So this Nima and Yara and Hugh studied in this paper. Proposed this in the paper, and also is very recently studied by Dean and Haslop. This is some amplitude hedron-like geometry, which has some issue when you take into higher and higher codimension residues. For example, you can define this object to be all these guys being positive, and this has k sign flips. And then the canonical form of this guy will be given by the product of nk MHV amplitude with its parity conjugate. But the canonical form is in quotation mark because there's really some subtlety here. So the square of the amplitude hedron is really summing over all these guys, which remove this sign flip condition. So there's no sign flip that you need to consider. So this should be a much simpler space, right? And all I want to say is that we need this, if we can compute this geometry, the form of this geometry directly, we should be able to, then we can extract this tree amplitude squares from the answer, which will be equivalent to all those very, very hard work from the F graph side. Okay. So there is one such attempt, which not only compute you the amplitude square, but directly going after the big object. Before you take any Lilac limit, can we find a geometric object that computes us the function that's symmetric in 4 plus L points, right? So I told you one way to compute that function is by bootstrapping F graphs, but there's this geometrical way, first considered by Eden and Haslop and Mason. But recently we reformulated this geometry and computed up to 4 loops. It seems that up to some, there's really a very strange way that we compute these things that based on considering these loop forms as some kind of fabrication of the tree-level kinematics. So here the kinematics space is really simple. You have some y that live in G4-8, and all this bitwister that live in G2-8, and you ask them to be positive. There's no sign flip condition anywhere to find. And at loop level, you're just basically asking this YAB xi and YABA ABB to be positive. So can you compute some kind of canonical form of this space? Everything is just the inequalities. There's no sign flip conditions. And the best way we found to compute this form is by considering at every point in your kinematic space some loop form. And then you ask, does the loop form change when you move from one point to another point in kinematic space? So this is what I mean by this fibration idea. At one loop, it's very easy. You see that when you go through the whole kinematic space, you compute the loop form, which is the loop form is just the canonical form of these conditions. This space carved out by these conditions is given by the one loop box. Very nice. But then you have to be a little bit careful because all you've done is in this square root positive region, this region. This is what we call the positive kinematic space. If you outside this region, the canonical form is actually 0. So actually here, there's already something interesting. You really should focus on this region where the canonical form is non-zero and outside it is 0. And since there's this roots come from this leading singularity of the 4-mass box is the square root of the quadratic equation. The final answer is given by summing over these 2 roots. Okay, so you have some tree form, which is just has a plus or minus delta in it. And then you have this one loop box you computed that also has a plus or minus delta. You need to sum over this plus and minus, and that gives you the final answer for the one loop correlator, where this prefactor is actually some all loop prefactor taking care of the non-renormalization theorem, and this is the one loop box in it. Okay? So we continue to 2 loops. Again, very nice. You compute the loop form. It's exactly given by the box square and 2 loop double box with some delta, plus or minus delta. So you just it with the tree form. The tree form lives in this positive delta region, and summing over the 2 solutions, you get the right 2 loop correlator. As I told you, this we have data in. So within this delta square positive, it's the same form. In the 2 loop case, it's still the same. Yeah, still the same. We're summing over just the 2 solutions when you, yeah, it's like a push forward. You're summing over the 2 solutions. But exactly, 1 and 2 loops is very special that there's no non-trivial chambers, that everything is just uniform in this kinematic space. So starting 3 loops is very interesting that when you scan through the kinematic space, you see that different points give you different loop forms. So this is the idea of the chambers. Yes. 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 There is a 4L forms. Yeah. Exactly. Yes. So we don't know directly how to compute tree plus loop, right? I mean, what we do is indirect way of at every point in the tree space compute the loop form and then just them with essentially the leading singularities of these different chambers. Yes. Finally, you need to sum over all chambers where so I mean naively a priori we don't know how many chambers are there. You have to go through the kinematic space, but you see that in one region the loop form doesn't change. So there's this chamber that has its own leading singularity, and then you multiply by the loop form, and then you sum over all the chambers. That's what we do. Okay. So for example, here is the chamber is defined by the collection of all the leading singularities being positive simultaneously. And this has been a powerful method that has been applied for computing loop forms of loop amplitude hedron. For example, for super mules, and also in this ABGM case, you realize that beyond MHV case, if you really look at the loop form in this perspective, if you go through the tree level kinematics, different points can give you different loop forms, and then you're summing over the chamber form times loop form, which is essentially the leading singularity multiplied some pure function, as we heard from other talks. But here you see that 1 and 2 loop is special because this maximal cuts are automatically positive everywhere in this region, so you don't need to worry. But for 3 loops, it's much more interesting. The whole positive region divided into 6 chambers, depending on the relative STU is some 3 variables of the brackets, x1 2 squares, x3 4 squares s, and the permutation give you t and u. It's really just the 3 factorial regions depending on the ordering. And exactly in any one of this region, you see that, for example, in the first region, when t is smaller than u and s, you see exactly that all these forms are, all the maximal cuts of this, all the possible maximal cuts at 3 loops become positive simultaneously. So you move to another one, it will, some other cuts will be, yes. External kinematic, yeah. At every point, you can ask the question, yeah. Yes. Geometry. Yes. So then you just ask, you then subdivide the kinematic space into these chambers. Each chamber is one that has one Wolfensohn on the loop side. Yes. And so then, so for each one of them, you have to count the form on each other. What do you do on the kinematic side? Now you have this chamber. Yeah, the kinematic side is essentially computing these maximal cuts. The kinematic side is just some tree data. So for every loop, for every chamber, you need to compute its own canonical form at tree level. Yes. Form some kind of positive geometry. Yes. 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 That's, yeah. And I'm just saying that how do you find all these chambers? You check the positivity of these maximal cuts. Yeah. So in this way, we recover the 3-loop correlator, which involve many different integrals. But our form of the the integrand of 3-loop correlator has the advantage that it tells you ahead of time what are the leading singularities, because they are just the canonical form of the chambers, and every one of them multiplies some d-log form in the loop space, which are guaranteed to give you pure functions. So that's one way to put it. So at 4 loops, there's some issue. So you go through this, everything is fine. You still find the 6 chambers, except you have an elliptic cut now. So actually, there is this cut. There's this cut that at starting 4 loops, depending on 4 internal points, that's elliptic. But that doesn't prevent you from fixing the full ansatz, but it's just a very weird thing, because we define the geometry, we define our chambers in terms of the positivity of all this maximal cuts, but there's something that you cannot cut to the end. There's some elliptic leading singularity that what does it mean for our chamber picture? We still don't know. In this matter still give you all the correct coefficient in front of loop integrand, but we don't know what this elliptic cut means. Of course, this elliptic cut goes away when you take the Lilac limit. So this geometry knows all about the 4-point amplitude hedron to all loops, if it's correct, right? It's certainly reduced to the 4-point amplitude hedron. And the main question is, can you how do you extract things out of it? For example, this geometry should also contain 5-point, 6-point amplitude hedron squared. But is there a way to really extract amplitude hedron rather than amplitude hedron squared? Or you go all the way down to tree level, right? It should contain that nice function. Sorry, yeah.
first time where you have local graphs with multiple numerators. So like, I guess you're just looking for all of the cuts and then whichever ones have support. How does it divide up according to the numerator state? Like, does it care about just the graph topology, or does it care about the dual conformal masters?
There are 3 F graphs, and 2 of them contain elliptic cuts. But when you write down all the dual conformal integrals for that F graph, only 1 of them contain elliptic cuts, right? So most of them are perfectly fine. Yeah.
I'm not asking about the elliptic. I just mean so through loops, every dual conformal graph, except for the duplicated points, some has a unique numerator on top of it, right?
Okay. Yeah.
But starting at 4 loops, you can have multiple numerators.
Sure. Yeah. Yeah.
How do you detect those differences? Or I mean, or maybe you don't. Maybe it doesn't matter.
I mean, for us, it's really from a geometry point of view, you really just compute some canonical form, which may or may not have multiple numerators when you expand in local integrals, right? So when you compute canonical forms, you don't know about those integrals. But it's just a for loop is also the first case we see some non-trivial things which may be related. I mean, we see this first of all, there are 3 F graphs, and then there are these multiple numerators and so on. Yeah. Right. So the main question is our definition comes from some definition that people propose, which treat all the 4 plus L points democratically, but that definition, no one has been able to use it for anything, right? So we have to take 1 step back. We pick 4 points that forms a kinematic space, and then we do this chamber thing, this fibration thing, to be able to compute the correct correlator. But the correlator is symmetric in all points. So that's really a big question here, that our way of computing things breaks the symmetry. I mean, is there a way to recover the symmetry? That we still don't know. And that's all I want to say about this loop integrand. So basically, there are 2 perspectives. One is concerns this just bootstrapping this F graphs, some combinatorics and graphical things about that. But the second one is, I think, is more interesting. Although we can only use this geometry to compute up to 4 loops now, it's just technical obstacles to go to higher and higher points. But this way of thinking is really makes you think. First of all, can you really define the geometry and compute the form in a way symmetric with respect to all points? And second of all, can you extract amplitudes, amplitude geometry? I mean, in a sense, amplitude geometry is a particular limit of this, right? So there's must be some connection. So finally, let me just mention some very quickly about integrations. So once you get this rational function that depends on all the 4 plus L points, you have several choices. One is what we physicists care most, that you integrate over all the loop punctures, you get some function of 2 cross ratios. At 1 and 2 loops, these functions are very simple. You heard from Jake, this box functions, and then there's some double box function. At 3 loops, in some very heroic calculation more than 10 years ago, they bootstrapped the 3 loop integral, the so-called easy and hard integrals, because these are some generalized polylog integral of uniform transcendentality 6 as 3 loop case, right? And actually, it depends on some very simple letters. The simplest integrals depends on z bar 1 minus z bar, which z bar are defined like that. These are so-called single value harmonic polylog. That's really the simplest you can get in this world. But starting 3 loop, you see some new letter like z minus z bar or 1 minus z bar. This extend this harmonic polylog into some single value multiple polylogs. And we're currently working on a bootstrap for the 4 loop case, which will be some transcendental weight 8 function of these letters. And the reason, I mean, why we should be able to do that is because we already classified all the prefactors. So that's the hard part. So you list all the prefactors, and for each prefactors, there's some weight 8 function there, depends on these letters. And we've basically bootstrapped all the multiple polylog part, but then there's the remaining 2 elliptic integrals. That's the thing we don't know. And there's also a lot of all loop results in this world. I mean, the most famous one is probably the ladder. The ladder is also always appearing as a special F graph in this game, and its integration is well known to be given by some classical polylog multiplying log. And there's also this class of diagrams known as Basel-Dixon fishnet, which generalize the ladder to some fishnet graphs. And very remarkably, this fishnet graph is given by the determinants of ladders. Okay, so this is something that's been understood from integrability on the physics side, but basically from something totally different. No one has been able to see even like, from perturbation theory, why this integral is evaluated to some determinant of ladders. Okay, so there's some understanding that the octagon picture from the integrability side actually directly extract you from the correlator something called the Coulomb 4-point Coulomb branch amplitudes that involve taking some Lilac limit in the 10D limit. So we found that this way of thinking is very useful because this provides you infinite number of predictions at higher loop level. The first case being this ladder integral has a symmetry, this so-called magic identity that people have been used in this conformal integral. But now there are really infinite number of such new identities which involve more than just two terms. There are more integrals are add up to 0 and so on from this point of view. And there's another object, of course, the even simpler object is that you integrate over all points. You don't just integrate over L point and depend on cross ratio. You can choose to integrate over all the 4 point plus L points. This will give you some periods, right? Some periods for this F graphs. So for each F graph, there's some, after you're integrating over all its points, it should give you some multiple zeta values. And this has been computed up to 6 loops, and this has some interesting correspondence with physics side, which is the also results from localization or from integrability that give you the sum of all these periods with the correct coefficient. That has been very simple. The sum of all these periods, there's a prediction that at L loops, only the zeta 2L plus 1 appear. Okay, and there's even some result about resumming them and compare with strong coupling. But there are two extremes. Whether if you sum it over all periods, then it becomes very, very simple. You know everything. But then the individual F graphs can have very complicated periods starting 5 loops, right? So we're asking, can this simplest ones, this fishnet, which you know the answer to all loops, can they have the nicest periods? Maybe. For the ladder, it has a very simple period, which is zeta 2L plus 1. But for 2 by 2, you can also show that it's zeta 2L plus 1. But starting 3 by 3, nobody knows the periods of all this very nice fishnet graphs. Okay, so that's all I want to say. Here are some outlook for, I think there should be very interesting things to explore about F graph and also including the non-planar part. For example, see this graphical rule, how constraining it is for non-planar sectors. And as I said, people have suggested me to look at, to ask machine to learn why all this F graph, majority of F graphs have 0 coefficient, but I still haven't given up on human to understand some why there's some pattern for all the zeros, I think. And of course, a very important question as I posed, which has physical application in this energy correlator, is how to compute tree level squared in a direct way. The BCFW is just really bad for this task. Like you have some, already at 8 points, squaring the 8-point BCFW takes a lot of work to bring it back to a local form. But we have results already up to 15 points. Is there a way to understand this tree amplitude squared as a very nice conformal invariant function directly from geometry? And there are also questions about correlate hedron and integrations that worth exploring. I'll just stop here. Thank you.
Any questions for Song? I have a question. Oh, sure, go ahead, Jim.
I just wanted to ask, have you looked into, in the energy correlation, when you look at the tree amplitude squared, do you see some structure, like at 6 points is pretty obvious, which is the MHV bar from the NMHV squared. But when you go up to higher points, you get a much more refined.
Yeah, very good question. Yeah. So up to, I think up to how many, like 11 or 12 points, you find that this function, this tree amplitude squared divided by the top form of the Grassmannian is given by always I mean, it's always a polynomial of these u variables, this cross ratio uij variables, but up to, I mean, each term should always be a monomial, but up to 11 points, you find it has only numerator. There's no pole, there's no uij appearing in the denominator. And starting 12 point, which is 8 loops, there is denominator. And we even check that those terms with denominator coincide with the term, with those F graphs you found that has divergence, the individual divergence. So I think there's really a lot of structure. Like 6 point is really just one possible cross ratio you have, and here you have 3 possible cross ratios. And whether or not, I mean, also there's even a constant piece, right? So as I said, naively we would say the constant piece is 1 at 6 points. So this 1 come from the MHV times MHV bar. This 3 cross ratio come from next MHV squared. But at 7 points, this 1 is cancelled by a -1 from the next MHV sector. And at higher and higher point, you see numbers at -5, 14, or -38 that appear. I mean, even just understanding this piece, when all the u goes to 0, you should have a constant, which is a constant you can extract from the chi amplitude squared. We don't understand that. Yeah.
So is it clear that your objects are dual conformal invariant? Like you assume that the x's are non-zero, right? So you can...
It's by construction conformal invariant, because it depends on all these points. And then when you take like limit, you go to the duality to amplitudes, which is also dual conformal invariant. So this object is really just defining the X space, which from the very beginning is conformal invariant. Yeah.
Conformal invariance acts on the X space, right?
Yeah. So when you say dual conformal invariant, you are thinking it as an amplitudes object. But that only makes sense when you take after you take the like limit, then you can. Correlation function is just conformal invariant, period. I mean, this will correspond to the dual conformal invariant in like limit, but yeah, it's a larger object that's conformal invariant. Yeah.
So this nice thing is you call the cross section. Of course, it's the Felicity summed cross section.
Mm-hmm.
The individual cross sections do make sense. So
Oh yes. Also the individual ones. Yeah.
So even in small examples, is there any way that you found to sort of project the specific? I mean, not go back to the amplitude, of course, but take the individual k, the individual terms in your sum, right?
Yeah, that's a very good question. I think that's one thing that F graphs doesn't know about. I mean, it's already the summing over all the k sectors. So the Amplitude square knows about it, because you can compute the part that has k sign flipped, and yeah.
The answer, is there some way to shove some kernel in there?
We don't.
Yes, just to extract the.
I think all I've been puzzled is that how. I mean, I haven't tried myself, but has anyone tried to compute the canonical form of these guys even at a particular k sector, right? And then adding them up will give you something even even simpler or even nicer. But individual ones is also very worth thinking about. Like, how do my here is very simple, right? How do this 3 cross ratio multiplied by the G26 top form is given by that thing? Is that obvious to some of you? I mean, I haven't.
These things, are they positive in the positive part?
No, because I mean, I don't know if about whether they are not positive or not, but since F graphs has minus signs, minus coefficients, so some terms have so their coefficient also always follow from F graphs. Yeah.
No, but it's positive in the positive part.
That I haven't checked.
Just a final quick thing. Something seems a little funny about this idea that I mean, it's very natural to find these chambers as you're moving around. That's great. But it's funny to take the form. I mean, to take the sum of all of those guys. I mean, it just feels funny because when you're in one chamber, when you're summing everything, you're getting a contribution from the forms in the other chambers.
But so for every chamber, you are computing its own canonical form. If you don't multiply it by the loop form, then and do the sum, you just get the form of the whole positive part, right? But now you're that's what I mean by fabrication. Now you need to weight it by the loop form and then sum it over all points.
I got that. I'm just saying that inside one chamber, the object you have is sort of tailored to the singularities that we would see there.
Right.
But
oh, you mean like other chambers?
But you're adding them all up together.
everywhere. There are some kind of, there is, unless maybe there's some positivity that stops us from happening, but don't the like, I don't know, the poles of another chamber. I guess the poles of the other chamber don't pass through this one. I guess they're just dividing. Okay, that's the claim.
Yeah.
That's the claim, is that just the positivity of all the leading singularities actually breaks the
Yeah,
kinematic space up.
it's really asking to go to the smallest block where everything is positive at the same time. Yeah.
More of a speculative question. So, I mean, when you go up to, I'm gonna make up some numbers, but like when you go up to 10 loops, you start having, the F graphs, they have two structures. They have the denominators and then they have the space of decorated numerators. And so far in this business, most people, we've always kind of just taken all possible monomials from the numerator, which corresponds to some graph with the numerator. But, 10 loops, there's maybe, a denominator with maybe 200 decorations on top of it. And 80% of those numerators have the same coefficient. And then there's another 20% or something that's different. I guess I've been looking for a while. Have you given any thought to how these different numerator decorations might be grouped together into some, clearly the sum of conformal things is conformal. Yeah.
Yeah, that seems interesting to think about. Yeah.
Questions for Sam? All right, if not, let's thank him again.